Okay, so let's take a look at 8.4 improper integrals. So integrals with infinite limits of integration are called improper integrals. So we have f of x is a continuous on the interval from a to infinity. Then what we do is we write, this is how it's written. Okay, so the integral from a to infinity of f of x dx. What we do is we basically change that to a limit as b approaches infinity, and then we evaluate the integral from a to b of f of x dx. Next we have, what if it's continuous from negative infinity to b? Then we're going to replace this lower bound. So we write the limit as a approaches negative infinity, and then we replace that lower bound with a, so we can evaluate the integral from a to b. And finally, what if both our lower and our upper bounds are negative infinity to infinity? Then we are actually going to rewrite it as the sum of two integrals. So we replace the lower and the upper, and then we evaluate those separately. Okay, so in parts 1 and 2, so here's 1 and 2, the limit is, if the limit is finite, the improper integral converges, and the limit is the value of the improper integral. So if we get a real number, then we know the integral converges, and the limit is the value that we get out. If the limit fails to exist, then the improper integral diverges. So that's with 1 and 2. Now, in part 3, the integral on the left-hand side of the equation converges. So this converges if both improper integrals on the right-hand side, so both of these converge. Otherwise, it diverges and has no value. So if one of them fails, so if one of them we get a real number, but then the other one we get infinity, then it diverges. The whole thing diverges. Okay, so example 1, we want to express the improper integral as a limit of definite integrals, and then B, evaluate the integral. So I notice that both the lower and upper bounds have infinity involved. So I'm going to rewrite this. So for A, the integral from negative infinity to infinity of e to the x dx. So I'll start with the lower bound, so I'll write that as limit as, now we can use a, we can use b, we can technically use any variable. I'm going to use b. So as b approaches negative infinity, we replace this from b to 0 of e to the x dx, plus, then we'll take the limit as b approaches infinity, and we'll have the integral from 0 to b of e to the x dx. So next what we want to do is we want to evaluate this. So we take these limits, and we have the limit as b approaches negative infinity. So what happens when we integrate e to the x? We get e to the x. We want to evaluate this from b to 0. And we get the same thing here, because when we integrate, we get e to the x. And we want to evaluate this from 0 to b. So we get e to the 0 minus e to the b plus the limit as b approaches infinity of e to the b minus e to the 0. So, well, what happens here, e to the 0, this goes to 1, right? So I have 1, actually let me rewrite this. Now, if I look at the first part, I have b approaching negative infinity. I can actually change this to b approaching positive infinity, and then this becomes 1 over e to the b plus the limit as b approaches infinity of e to the b minus 1. So we get 1 minus 0 plus infinity, basically minus 1, which equals infinity. Therefore, it diverges. I think the second part diverged. Example number 2, evaluate the improper integral or state that it diverges. So now we just have the upper bound to worry about. So first thing we're going to do, we're going to rewrite this limit as b approaches infinity. And then we have the integral from 1 to b of 1 over x dx. So we integrate. That means we end up with ln would be absolute value of x, but since it's 1 to b, we already know it's going to be positive. So notice I just keep writing the limit until I've completed everything that I can do with the integral. So here we're going to have ln of b minus ln of 1, which ends up being 0. So I get ln of infinity, which goes to infinity. Therefore, it diverges. Next we have b. So I'm going to rewrite this, the limit, as b goes to infinity. And then we have, now I also see that I have a 3 here. So actually, before I even do that, I'm going to bring the 3 out in front. So I have 3, limit, b goes to infinity, the integral from 2 to b of 1 over x squared minus x dx. Now, I would think of using u substitution here, but that's not going to work because the derivative of the bottom is 2x minus 1. So instead we have to think back to when we did partial fraction decomposition. So over here on the side, I'm just going to look at this part. So I have 1 over x times x minus 1. So I want to rewrite that. I have a over x plus b over x minus 1. So I have a times x minus 1 times b times x. That has to be equal to 1. So if I let x equal 1, I get b equals 1. If I let x equal 0, I get a is negative 1. So when I rewrite this, I have 3 limit as b goes to infinity, and the integral from 2 to b, and I'm going to have negative 1 over x plus 1 over x minus 1 dx. So I get 3 limit as b approaches infinity. Now I'm going to take the integral, so I have negative ln of x plus ln of x minus 1, and we want this whole thing evaluated from 2 to b. Now I could just simplify inside of here, so actually I get 3 limit as b goes to infinity. That's going to be ln of x minus 1 over x. And we want to evaluate this from 2 to b. So now let's evaluate the limit. We have ln, so that's going to be b minus 1 over b, minus ln of 2 minus 1 over 2. So this, oops, somehow I lost my limit as b goes to infinity. So here if we take a look, has the same degree at the top and the bottom. So we think of what happens here as b goes to infinity. We get a common ratio, or sorry, the ratio of the leading coefficients goes to 1. So I have ln of 1 minus, and this will be ln of a half. So that's going to give us 0 minus ln of 1/2, which is really just negative ln 2, so I get 3 ln 2. Next we have the integral from 1 to infinity of x e to the x, negative x dx. So I'm going to rewrite this limit as b goes to infinity, the integral from 1 to b, x e to the negative x dx. Now this, not a u substitution, this is actually an integration by parts or tabular method. I'm going to go and use tabular method since it's pretty easy to do. So we're going to do the derivatives along the left side, so it's 1 and then 0. And then I'm going to integrate, so that's going to be negative e to the negative x, and it's going to be e to the negative x. And then we go diagonally, and it goes plus, minus. So now I get limit as b approaches infinity. I'm going to have negative x e to the negative x minus e to the negative x, and we want to evaluate that from 1 to b. So I have negative b e to the negative b minus e to the negative b minus, then I have negative 1 e to the negative 1 minus e to the negative 1. So let me just rewrite this. This gives us negative b over e to the b minus 1 over e to the b. And then this actually gives us a plus 2 over e, because I have 2 of those. Now, as b approaches infinity, take a look, we have b over e to the b, so that's going to go to 0. And 1 over e to the b, that's going to go to 0. So we're just left with 2 over e. Okay, we have another example, D. So again, from negative infinity to infinity, so we're going to rewrite this as 2 separate ones. So I'm going to have the limit as b approaches negative infinity, so we have b to 0, 1 over 1 plus x squared dx, and then plus, then we have the limit as b approaches infinity, and that's going to go from 0 to b of 1 over 1 plus x squared dx. Now, hopefully you recognize can't use u substitution, can't use integration by parts. This is actually the antiderivative for tangent inverse. So I have the limit as b approaches negative infinity. Oops. So when we integrate, we get tan inverse of x evaluated from b to 0, and then we get the same thing here. The limit as b approaches positive infinity, tan inverse of x evaluated from 0 to b. So I have tangent inverse of 0 minus tangent inverse of b plus, and then we have the limit as b approaches infinity, tangent inverse of b minus tangent inverse of 0. Now, tangent inverse of 0 is going to give us 0. And now the next part's kind of tricky because the tangent inverse of b. So as b approaches infinity, we think about the graph of tangent. So tangent, right? Tangent has asymptotes at negative pi over 2 and pi over 2. So it looks like this. So we're kind of looking at this part. So as b is approaching infinity, because remember tangent inverse is just the reverse. So tangent inverse, as that's approaching infinity, we're actually getting closer to pi over, sorry, this is negative infinity. I keep forgetting. Negative infinity. Let me go back. So actually negative infinity this way is getting closer and closer to negative pi over 2. Sorry, I forgot my negative sign there. So that means over here, I'm going to have as as b approaches infinity, we're approaching a pi over 2. And then this is going to be minus 0. So we get pi over 2 plus pi over 2. So our answer is pi. Okay, so we may, instead of an improper integral involving infinity or negative infinity, we could have a case where there is a vertical asymptote, an infinite discontinuity. So let's take a look at something like 1 over square root of x. So if we want to consider the region, right, in the first quadrant that lies under that curve from 0 to 1, but at 0, there is a vertical asymptote. So what we do is we figure out, okay, well, maybe we don't want to start from 0. Maybe we want to start from some value a. So if we can figure out the area of this region, right, so why don't we do that? Let's figure out. So this is x to the negative 2, so it becomes x to the 1/2 over 1/2, so it becomes 2 root x. We want to evaluate that from a to 1. So we have 2 root 1 minus 2 root a, which is 2 minus 2 root a. Now, what we want to try to do is say, all right, as a gets closer and closer to 0 from the right, what is that value going to be? So we get limit as a approaches 0 from the right. Now we already said that when we evaluated that integral, we got 2 minus 2 root a. So we get 2 minus 2 root 0, which is 2. So therefore the area under the curve from 0 to 1 is 2. Kind of neat. So that's another way that we use improper integrals. So with these infinite discontinuities, okay, if something's going on here at a, we'll say, oh, c approaches a from the right. What if it's continuous from a to b, but b is the infinite discontinuity, so we approach b from the left. And then what happens if there are situations where we have infinite discontinuities at a and at b, then we separate it into two different integrals. Okay. So parts 1 and 2, again, very similar to the last one. So if the limit is finite, then the improper integral converges, limit is the value, the limit fails to exist, improper integral diverges, and then for part 3, we need to make sure that both of them converge. Otherwise, it diverges. So example 3, state why the integral is improper, and then we want to evaluate or state that it diverges. So if you see that in the denominator, if x is equal to 1, we're going to have a vertical asymptote. So there's a vertical asymptote at x equals 1. So it's continuous on the interval from 0 to 1, excluding 1, and then 1 to 3. So what we're going to do is we're going to break this up. We're going to make this into the integral from 0 to 1 of 1 over x minus 1 to the 2/3 dx, plus the integral from 1 to 3 of 1 over x minus 1 to the 2/3 dx. So we have to think about at 1, okay, so we're going to introduce the limit. I'm going to say as b approaches 1 from the left is going to be the integral from 0 to b. And I'm going to rewrite this as x minus 1 to the negative 2/3 dx. And then I want to add the limit as b approaches 1 from the right, the integral from b to 3 of x minus 1 to the negative 2/3 dx. Okay, so b approaches 1 from the left. So we integrate x minus 1 to the negative 2/3, so it's become x minus 1 to the 1/3 over 1/3, or 3. And then it's going to be x minus 1 to the 1/3. We want to evaluate that from 0 to b. Next is going to look exactly the same, except here it's from b to 3. So let's plug in our values. And the 3 can always be moved out in front if we want. So actually, let me do that first. I'm going to move the 3 out. So I have b minus 1 to the 1/3 minus negative 1 to the 1/3 plus, and then here, I'm also going to move the 3 out in front. So I have 3 minus 1 to the 1/3 minus b minus 1 to the 1/3. So now, as we look at our limit, so as b approaches 1 from the left, this is going to give us 0. So I have 0 minus negative 1, so it's going to become plus 1, plus 3. And then here we get 2 to the 1/3, or cube root of 2. And then this whole thing is going to go to 0. So we get 3 plus 3 cube root 2. Alright, again here, in this case we have a vertical asymptote at x equals 2. So it's continuous from 1 to 2, excluding 2. So I'm going to rewrite this limit as b approaches 2 from the left, the integral from 1 to b of 1 over x minus 2 dx. So in this case, I'm going to have ln of x minus 2. We want to evaluate this from 1 to b. So we get limit as b approaches 2 from the left, that ln of b minus 2 minus ln of 1 minus 2 And so therefore we can see right away both of these. This is going to be ln of 0. That actually does not exist. This actually approaches the value of negative infinity. So this diverges. Okay, so sometimes we cannot evaluate an improper integral directly. Okay, so we want to decide whether it converges or diverges. So if the integral diverges, then we're done. That's the end of the story. If it converges, we can then use numerical methods to approximate its value. All right, so here's the following theorem. We're going to use a comparison test. So let's say we have f and g are continuous on the integral interval from a to infinity, where f of x is between 0 and g of x for all x greater than or equal to a. So if f of x converges, f of x converges if g of x converges. And again, think of this as the bigger one. So if the bigger one converges, then the smaller one converges. And this one is, now what if the smaller one diverges? Then the bigger one diverges. So if smaller one diverges, then the bigger one diverges. Okay, so here's what we want to do. This one we have x cubed plus 1 in the denominator. So I'm going to compare this one to 1 over x cubed. Okay, and we want to look at this on the interval from 1 to infinity. Now, 1 over x cubed converges. We know this. Let me just show you on the side. So this would be x to the negative 3 dx, so we get x to the negative 2 over negative 2, so negative 2 over x squared. So we get, basically, as plugging in b, so we get b squared minus 1, so negative 2 over b minus negative 2 over 1. So this is going to go to 0. We get 2. Okay, so that's going to converge. So if the bigger one converges, then we know this one must converge. So therefore, 1 over x cubed plus 1, the integral from 1 to infinity dx, also converges. Okay, so for part B, first thing, we want to split this up into 2 times the integral from 0 to infinity, 1 over square root of x to the 4th plus 1 dx. So in this particular one, we're actually going to split this up because at 0, it's not going to work. So we're going to rewrite this as 2, then the integral from 0 to 1, so 1 over the square root of x to the 4th plus 1 dx. And then we're going to add the integral from 1 to infinity of 1 over square root of x to the 4th plus 1 dx. So that really this is all we need to look at. Now, this is a proper integral. So this we already know, this is going to converge. So the one in question is the 1 to infinity of 1 over square root of x to the 4th plus 1. Now what I want to do is I want to compare 1 over the square root of x to the 4th plus 1. I want to compare that to 1 over x squared. Now, I know we don't have a lot of room, but will this 1 over x squared, will that converge? So if I consider the limit as b goes to infinity of x to the negative 2 dx, the integral from 1 to b. So we get negative 1 over x, keep forgetting to write my limit as b goes to infinity of negative 1 over x, evaluated from 1 to b. So yes, as we look at that, we'll get negative 1 over b minus negative 1 over 1, or plus 1. So this does equal 1. So therefore, since the larger one converges, then this converges. So since both parts converge, then the whole thing converges. So therefore, the integral from negative infinity to infinity of 1 over x squared of x to the 4th plus 1 this converges. Okay, example number 5. We want to use the arc length formula to show that the circumference of the circle, x squared plus y squared equals 4, is 4 pi. I am probably going to skip this example for now. If you look in your notes, the notes that are posted on Haiku, you can see a full worked out solution for that. I'm not going to really worry about it because you're never going to have anything like this on the AP, and you're not going to have it. I don't think I gave you any problems like that for homework. So let's look at the very last example, example 6, because this is where sometimes we have the volume with these improper fractions. So we want to find the volume of the solid obtained by revolving the curve y equals x e to the negative x from 0 to infinity about the x-axis. So we picture this, that's our r. Now, our area, right, so if this is a rotating, then it's going to be pi r squared. So my volume is going to be pi, and then it's going to be the integral from 0 to infinity of x e to the negative x squared dx. Okay, so I want to rewrite this. I'm going to put pi out in front. We have the limit as b approaches infinity, the integral from 0 to b. And I'm actually just going to multiply that out. X squared e to the negative 2x dx. This, again, this could be integration by parts for tabular method. I'm going to do tabular method. So I get 2x to 0. There I get negative 1/2 e to the negative 2x, 1/4 e to the negative 2x, and negative 1/8 e to the negative 2x. Alternating signs. Okay. So we get, and then put my equal sign over here to make more room. So I get negative 1/2 x squared e to the negative 2x. Then I get minus 1/2 x e to the negative 2x. And then minus 1/4 e to the negative 2x. We want to evaluate this from 0 to b. Okay, so there's quite a bit of factoring out. I can factor out an e to the negative 2x, and I can also just do a little bit of algebra. So I'm going to kind of clean this up here. I get negative 2x squared minus 2x minus 1 all over 4e to the 2x. Actually, let me put brackets. So that, double check to make sure that's what you get. But basically what we end up with is a polynomial over an exponential function. So we know, even if I replace all the b's here, negative 2b squared minus 2b minus 1 over 4e to the 2b. And then, of course, if we plug in 0, let's see what we get. Well, we get negative 1 and then 4th on the bottom. So all of this in that first fraction, as b goes to infinity, this whole thing, right, this whole thing is going to go to 0. So we get pi, and that'll be a positive 1/4. So we get pi over 4.